Okay, so today what we're going to do is what is called matched pairs, which is different from anything we've done so far. I like to think of this in a sense as the before and after. So we're not comparing Mesa College to City College and say which gets more sleep. I think that was one of the questions you had on the quiz. Or I'm not comparing Ava and McKinley's free throw shooting skills, right? That's a comparison of two different people. No, actually this would be more like you're going to take a course, maybe it's an SAT prep course, and you want to measure, did you improve? You're going to a weight loss clinic and you want to measure, did you actually lose weight? Does everybody understand it? It's you have two numbers, a before and an after number. Or we could simply be comparing, males versus females within this class, after a test. That's one way of looking at it. I think the before and after is far more effective. So the idea being, if you were trying to measure the effectiveness of something, pharmaceuticals. Okay, this is probably where this is the biggest. How do you know if a drug actually works? Anybody want to try that one? I mean, there's a new drug on the market. It had to be approved by the FDA. It probably took years and years and years of testing. So how do we know if it actually works?
The double blind.
Okay, so what does that mean exactly to you?
We test a placebo and then a control and don't tell either of them which one they have.
Okay, that's probably the most common.
Yeah.
Powerful. So the idea being, all right, so I got a shot in Isaiah. You guys, I'm going to give you both. Now let's say you're not dying of something. Maybe I have a weight loss pill or a pill to improve, I don't know, I don't want to say a PED, but improve performance naturally. How's that? And so I give you both the pill, and I measure you before, and then I measure you after you've been doing it. Well, the fact that I'm giving you a pill and saying, this is going to improve your performance, guess what's going to automatically happen? Automatically. Your performance is going to improve some. Why? Because you believe it's going to improve. So what the placebo is I give you something that you think is the pill or the medicine or whatever it is. You think you're getting the treatment. But one of you is getting it, one of you is not getting it. But as Dylan said, the double blind is I don't know who's getting it and you don't know who's getting it. So that makes it more effective. There'll be some code, some label, so we can track, But when I'm giving it to you, I don't know which one is the real thing. So I'm giving you both it. You both believe you have it. And now I'm going to measure the performance. I'm going to measure your improvement versus not each other, versus yourself, before and after. Now, one of you is getting the placebo, one of you is not. If both of you improve roughly about the same or similar amounts, does that mean the drug worked? No, actually it means the drug didn't work at all. Because if you took a placebo, you thought you had the drug, you improved just as much as the person who had the drug, that means the drug doesn't work at all. That's why it's so important that we do this type of testing. Now, one of you had the placebo, one of you didn't, and the one who didn't have the placebo, the one who had the real thing, had a way bigger improvement than the placebo person. Now, would that mean, hey, that probably works? So, of course, I'm going to test this brand new thing, for years and years and years on exactly 2 people. No, I'm probably going to test it on hundreds of people, right? I'm going to have a really large test. And then I'm going to say, what is the average performance for the placebo group? What is the average performance for the actual real group? And that's how things are done in a simple sense. Now, this would be something that is not, you don't have a life-threatening disease or something like that. Now, here's where it gets a little bit iffy. And it used to be different, but you have cancer. You are dying of some ailment. And I want to test a new cancer treatment. If you're dying of cancer and I have a new drug that might cure you, you want the new drug that might cure you. You don't want the placebo. So in other words, we don't do it exactly the same way. If it's a terminal illness and we're trying to test a new drug, we don't do the placebo thing because the people with the terminal illness are now going to die because the placebo isn't going to help them overcome the cancer or whatever it is. Believing your performance will improve on something is different than actually attacking cancer cells. You understand this? They're not even similar concepts. So we don't typically do the placebo, kind of effect. So what we'll do is test. Now, in cancer treatment, it's very interesting because, again, this is one of the most common types of before and afters. So what they usually do in this situation is they have people who are terminally ill. Terminally ill would mean they've given you a diagnosis of probably less than 6 months. The cancer's that far gone. And if it were you, you'd say, yeah, I will take a chance. This stuff may make me very sick. I mean, chemotherapy and radiation generally makes you very, very sick, but it also can be effective. So I've got this thing, and you're willing to try it, and so we try it on you. Now, it might not work, but it also might work. Now, how do we measure whether something worked if you're giving it to terminally ill patients? Do they have to be cured? What do you think would be a good measurement to whether my cancer treatment was actually effective or not? If let's say you're given a diagnosis of less than 6 months, because this is actually very common.
Living past 6 months. Living past 6 months.
That's actually the simplest way to look at it. If you've got extra life. In other words, you had a diagnosis of you were terminally ill and you lived an extra couple of years. You'd say, then that was really effective. It didn't cure you, but you got a lot of additional time. Now, what do we call cured in cancer?
Remission.
But what is there a line in the sand? Do you know what it is? It depends what it is, but you know, the usual line in the sand is like 5 years. You have been cancer-free literally for 5 years. Might you still die of cancer later on? Yes, but if you were given that terminal diagnosis and 5 years has passed, they generally said you've beaten it. And so the idea is, how do we know if the drug was effective? Well, like McKinley said, did you get extra time out of it? So this is what I mean by the before and after. We measure your situation before something, and we measure it after something, and we look at the difference to see, did the thing actually work? So we're going to do a really simple example. And I'm going to use an example this actually happened. We had a tutor at Mesa College. He was a former student of mine many years ago. Wasn't that good of a student. I mean, he literally took all the calculus classes, but he'd take every one of them like 4 times. Because he didn't pass them. And so I had him in a couple of calculus classes, literally like 3 or 4 years apart, because he was taking everybody under the sun. But he was, you know, eventually we get a C in everything. But he was a Mesa College tutor for many, many years, but he did a lot of private tutoring on the side. It was kind of a snake. He would work in the Mesa tutoring services, you know, get paid by Mesa College to try to recruit people to hire him privately. And then that's how he made all his money, the private tutoring. But one of the things that I had is, he'd ask if he can deliver his brochures and his pamphlets to class. One of the things, he guaranteed improvement in any math course. He actually had a number, like he guaranteed 20% improvement. Now think about that. Guaranteed you 20% improvement. That's pretty impressive. Can that be tested, you think? Especially because he actually had a lot of people who would hire him. And his favorite line was, oh, your instructor doesn't know what they're doing. I do. This is what he'd tell people. This is the guy who would take 4 tries to get a C in every class. He was telling the students that the instructors didn't know what they're doing. So he was kind of I think they call it a snake oil salesman, you know, back in the day. But, you know, there were some people that thought he was a terrific tutor, and most of the math faculty despised him because he basically threw everyone under the bus because he'd had almost everybody in the math department at some point. So we're going to test the claim. So let's just say Biff the math tutor, by the way, his name was not Biff. Biff the math tutor claims he can improve your performance in math class by 20%. Now, it's easier to do a percentage than it would be a score, wouldn't it? If I said you can improve by a certain score because, you know, is it a 100-point test or is it a 1,000-point test? It's not the score, it's the percentage. So he claims he can improve your percentage by 20%. Does that mean he's, again, this is one of these areas we've discussed a million times. So is he saying he's going to improve you exactly 20%? How would you read that? Is this an equals or is this an inequality? What's he saying? I can improve you
20% or more.
Does everybody agree with that? At least 20%. See, if you improve 30%, are you going to ask for your money back? But if you only improve 10%, yes, then you're going to ask for your money back. So when he says, I can improve you 20%, we know that's an implication. Without using the words 20%, we automatically know that's at least 20%. When the manufacturer says you're going to get 40,000 miles on your tires, they're saying you're going to get at least 40,000 because more is fine, right? More is okay. Less is bad. So this is what the claim is. But so then what would we do? And how would we measure this? Well, let's first figure out how would we set this one up? And so let's test at the, let's say, alpha 05 level. And again, the wording of significance. This is not some, cancer treatment, life and death drug. That would be 1% if it were something really, really serious, but 5% is fine. So what is it he's claiming? Is he saying the average person? Yeah. He's saying that you individually, but on average. So how would we do it? What we're going to do is we're going to have a before and we're going to have an after for each person. So what we're actually measuring, we're not saying let's take a group of people, let's take the average of their performance. Now let's take the group of people after they've had tutoring, let's take the average of their performance and let's see if that's 20%. No. We take each individual, we measure their difference, and then we average the differences because we do the standard deviation based on the differences. Individual. So the way we write it is, I'm going to give you a slightly different symbol. We say mu of the difference. And we put a subscript of D. The D is difference. The average difference he's claiming is at least, and I'll write it, actually let me put it in terms of percent. I'll write it in percent. Is at least 20%. So the alternative would be that the average difference is less than 20%. So we're not saying the average person, we're saying the average difference for each person. So every single person will have a pair of numbers. Now this, I just talked about cancer treatment a moment ago. It's the exact same idea. There's a measurement that takes place before, there's a measurement that takes place after. The only number we care about is the difference. So let's say, for example, that he's claiming he gives you 20% difference, but you're already getting 90% in the course. So he's going to have to get you up to 110%, isn't he? But if you're only getting 30% in the course, then he's only got to get you to 50%. So we're not averaging your percentages coming in. We're only looking at the differences. So whether you're at the low end or you're at the high end coming in is irrelevant. It's what is the difference, okay? So this is how it's going to look, and I'm going to give you the numbers in a moment. Now, we need to know, by the way, how many people are involved in order to know what to look up. Do you think this is going to be a Z or a T?
T.
It's going to be a T because we don't have, first of all, we don't have a population standard deviation that we could even look at. We're actually going to just be looking at the test individuals. It is reasonable to say that improvement is probably normally distributed. We don't expect extremes in either direction. That's an easy way to think about things. Things do not have to be perfectly normal. We say essentially normal. Human heights are essentially normal. If we looked at the entire world, they're essentially normal. Improvement in this area, yeah, you're not going to have a whole bunch of people that are off the charts where everyone else is, or a whole bunch of people that went the other way. You'd say, you know what, it's probably reasonable that they're going to be fairly evenly spread out. It doesn't have to be perfectly normal, just essentially normal. And why is that important? Because if I don't have the normality, then I have to have samples of at least 30. Now, what if we actually had 100 matched pairs? Then does it matter if it's normal or not? No. But for the purposes of doing a problem like this, we don't want to have 100. That's a lot of calculations. Okay? And it might actually be difficult. Again, we talked about cancer treatments and things like that. There are terminally ill patients. Or maybe it's a really, really rare disease. Now, this is a problem. It's a really rare disease, and we're trying to determine if our treatment works. Well, if it's a really rare disease, am I going to be able to have a large sample? No. In fact, it's a really rare disease. Well, I'll just get all the people who have the disease. That means I might be gathering people all over the world in order to get that's not practical. Oh, so there are times when I have to deal with smaller samples. Now, if the normality clause, if there's no way I can even consider that, it's a totally different problem. And I said that's the problem we do not touch in this class. In fact, when I did graduate school at San Diego State in statistics, it's the highest level class in statistics, they said, in the entire university. It's called non-parametric statistical methods. And it's a 700 course, by the way. There aren't a whole lot of 700 courses. 700 courses is actually like after grad school, kind of. And it was gnarly, and it's what you do in those cases where you only have a few. The calculations are horrific. There's a section in our textbook at the end where he actually mentions non-parametric statistical methods, it's called. It exists. I don't ever need you to worry about that because it is so rare. Again, it's the rare illness situation where you have so few. Right? That's not something that comes up a lot. So that's not something we would do in this class. If you decide to go and do graduate level work in statistics, then you'll have to take that class. Right? But that's probably a couple semesters away. You agree? Okay. So let's say that we end up with, let me give you simple. We end up with 10 matched pairs. We're able to get a sample of size 10. So now we need to look up our line in the sand. We agree that it's going to have to be a t-value because we're going to be only using the sample information. We're going to have a sample standard deviation at some point. So I need the line in the sand. We said 5% level, it's a one-tailed test. How many degrees of freedom? 9. So go to your t-table. Look up 9 degrees of freedom, 5% tail. What is my magic number there? 1.833. Now, he's claiming to be really, really good. We will reject his claim if he's really, really bad. So we will reject the null hypothesis if what? If our measured t is, always look at the alternative, right? The rejection comes from the alternative, not from the null. So we will reject if our measured t is
less than negative 1.8.
good, less than the negative. You see, what if we do a sample and those people did not improve 20%? They only improved, 19.5%. Right? You realize if it's close to 20%, that's not enough to fail. But I take a group of people and they're way below 20%. That would be enough to fail. What if I took a group of people and they were way over 20%? Well, then obviously his claim is valid, isn't it? So let's look at the matched pairs. So here's what we have. We'll have the before, we'll have the after. And I'll make it simple. I'll just do percentages as integer values, okay? We're going to do a few of these kind of problems today. So the before people, this person was at 62%, this person was at 83%, this person was 57, this person was 74, this person was 46%, this person was 93%, this person was 48%, 55%, 67%, and 82%. Okay. These are people who hired Biff the tutor. Now, this person here made it up to 77%, this person to 89%. This person here went all the way up to 78%, this person to 89%. This person made it up to 63%. This person basically stayed the same. This person here made it to 70%, this person to 68%, this person to 76%, and this person to 90%. So we have a sample of size 10, and this is what we see. So, do I average these numbers on the top? No. Do I average these numbers on the bottom? No. How much did they improve?
15?
15.
6. 9? No, 11.
How about 20?
20.
We're getting it. 15,
Too early.
I can't do math like that.
17,
9.
0 out of that. 12.
22, 13, 9, there's your 9, and 8. I average these numbers. That's the whole point. I only look at the changes. Everybody got it? Now, by the way, does it matter which way you subtract? Well, yeah. If I subtract backwards, then all these numbers are going to be negative, aren't they? It's going to be really hard to work with if I subtract. And you're saying, you're laughing, well, when would you do that? We're going to do weight loss next. And you actually do subtract in the other direction for weight loss. Oh, because if you're trying to measure a decrease, then you measure differently, don't you? But here we're trying to measure improvement. So we're actually looking at the improvement. So we're going to look at these 10 values. And now the notation we're going to use, I need the sum of these are the differences, by the way. So I need the sum of the differences. I need the sum of the squared differences. I need those first. So let's do that on your calculators. Tell me when you get a number.
126.
Okay, you all get that? And then sum squared. I like just doing this right off the bat. You're going to have to do this on your own. That's why we're going to use typically small data sets, because otherwise it just takes too long. What if I have a great, powerful computer? You still have to enter all the numbers, though. It still takes too long. Tell me when you get a number there.
2014.
2014, okay. So there's that's called summary data. Often this is provided. During an exam, I'll usually provide this just to save some time because we know what to do with it. So now I need to do two calculations. I need the X bar of the differences. The reason I'm putting the subscript of the differences, look at right here. Doesn't each person have exactly 3 numbers associated with them? They had their percentage before, their percentage after, and the change in their percentage. So I'm saying, oh, I'm only looking at the differences. Because if I said, let's average the befores, there's nothing wrong with that, but that's not a number that I'm going to use to do this problem. So this will be 126 over 10. Beautiful. What's the variance of the differences? Okay, so it would be 2014. 10 times 12.6 squared over 9. Sometimes we forget the formula. We should know this one. This is the formula we've used more than any other formula probably, right? Sum of the squared scores minus n times x bar squared over n minus 1. And what does this come out to be? Bring a number. Oops. I just hit something goofy on my calculator. Oop. I actually lost it. There we go.
Oops.
47.3.
Oh, it's that, right?
Yeah.
Now, right now that doesn't mean anything to us, but we're going to be using this in a calculation in a moment. Now, don't round off. Use the number on your screen. And it's funny, I was just doing this with a class yesterday in one of the other classes I'm teaching. We were doing something that had lots of calculations, and they're like, well, it takes forever to keep re-entering the numbers. And I said, why would you re-enter any of the numbers? You already got it on your screen. You have a key. Your favorite key is the answer key. Does everyone know you have a key on your calculator, meaning you never have to re-enter the calculations? You just use the answer key. So when we do the standard deviation, we're going to take the square root of the answer key. We're not going to re-enter the decimal and then take the square root because that leads to inaccuracies, round-off errors that we don't need. No. So I reported it. Now I need to do the calculation. So how does the calculation work? Well, the same as it always has. It's going to be x bar minus mu over what? Standard deviation over root n. I mean, we know that. Oh, okay. So what was my x bar? 12.6. What am I subtracting? Remember, we're saying 20% is the law. and we're gonna see if the evidence shows otherwise. We've never said that before, have we? Oh, okay. Our sample, we're gonna start by assuming, yes, it's 20% improvement, and let the sample show us otherwise. So we are starting with, no, we're gonna say 20%. Now, what goes down here? The square root of this over
Population.
what? Over n or over root n?
So why are we putting 20 there and not 0.2?
Oh, because I was doing it as whole percentages just to make it easier.
Oh, okay, all right.
You know, I was saying
That's a
48.
percentage, not a number, right?
I was saying 48%.
Yes, gotcha.
Yeah. Well, I'm glad you asked that. These were not scores. These were the incoming percents. By the way, we could do these as decimals. That would be fine.
Yeah.
But what would change? Obviously, this would now be a decimal.
Right.
This would be a much smaller number. In other words, will it change our calculation here? Actually, no, because all of these numbers would be adjusted appropriately. If we use decimals, our t will still be the same calculation. It just, if we can measure in terms of whole percentages rather than decimals, this is odd. In a math situation, we would normally use all the decimals. But it just makes all the individual calculations a little bit messier without changing the answer. Right? It'd be kind of like we're talking about heights, and we start getting into the minutia of, let's say we're using metric, and so McKinley, you're 1.93 meters. Well, why not just say 193 centimeters? Wouldn't that be easier? And by the way, is that the same height? Yeah. Why would in the world would we use a decimal value of meters when we can use an integer value of centimeters? So in other words, that's what I'm talking about. Let's keep the calculation simple without changing the problem. So what goes here? Square root of n. So let's do that. So I'm going to take the square root of my answer. Tell me when you get a number. I got a number. And it's negative, by the way. Right? Can't see it, tell you. I think we got something went wonky here. Remember, this is s squared, so you can take the square root of this ultimately, right? The square root of this is a little less than 7.
Negative 3.4. I got it.
That's what I was saying.
Negative 3.4?
Yeah.
Does it matter how many decimals I put? Not really. Why?
Because you're
Yes,
already
it is.
If it were close to that number, then the decimals would probably be more important. Do you all agree with that? Now, negative 3.4. What does that look like? You are here. Are you in the shark-infested lava? Oh, you're way out. You were rocket launched in the shark-infested lava. Now we love this kind of situation in stats. There's no ambiguity. There's no judgment call. Guilty? Oh, yes. In other words, will we reject the null hypothesis? Easily. Yeah, soundly. Not even close. We don't say things like, well, the evidence says that it's probably the case that we reject the null hypothesis. That's like saying, the evidence says you're probably guilty and probably deserve the death penalty, so we're pretty sure we probably are going to go ahead and execute you. No, I don't think it works that way. You're guilty. We don't say, yeah, you're probably guilty, you're likely guilty based on the evidence. No, when we say guilty, that's absolute. Not guilty is where it's iffy. No, guilty is absolute. There's no gray area. If you're guilty, period. Now you get the punishment. We reject the null hypothesis. That's a no-brainer. Why? Because we're not even close. I mean, here is the gray area. We were way the heck out here. So our conclusion is, reject the null hypothesis. Therefore, what is the truth?
It does not improve the formula by 20%.
Yeah, or more simply say, the improvement is going to be much less than 20%. Probably would be safer. Because if we're just saying, well, he doesn't increase 20%, that sounds a little vague. How about, no, the improvement is much less than 20%. Now, do you see how we did the problem? This is different from anything we've done because of the way we did it. Normally, when we have two sets of numbers, we were comparing, right? We were comparing Ava and Ashad's free throw skills versus each other. Okay, that's a simple comparison. There's no before and after. One of you doesn't become the other person, and now we say the difference is, no, I'm comparing. We compared Mesa College to City College in terms of who gets more sleep. That's easy. So I take the average of one group and I compare it to the average of another group. Right? I'm just looking at numbers. But now I'm trying to measure the effectiveness of something. You see, that's a totally different animal. How do you know if something's effective? Well, you have to do a before and after with the same thing. So if we're trying to measure the effectiveness of a drug, as Dylan pointed out, yeah, we're going to do all these types of testing, you know, these random, double-blind, all these are fancy names, basically making sure there's no bias. That's what it really is. See, if I said, well, I know who's getting the placebo and who's not, and I know Ava really reacts well to everything, so I'm going to tell her I'm giving her the drug, but I'm actually going to give her the placebo, it kind of defeats the whole purpose. Because I already know what's going to happen. No, I don't want to know. But that's just how you do the test. But ultimately, when we're trying to measure the effectiveness of something, whether there's a placebo or not, to measure the effectiveness of something, I have to take a measurement before you do it and a measurement after you do it and see, is there a change? And is the change in the right direction? And is the change significant? Let's suppose everybody here, they went to Biff the tutor and they said, oh, I'm going to Biff the tutor. I hear great things about Biff the tutor. Are you going to improve with that attitude? Probably. Yeah. Again, the whole placebo affected, oh, I'm going to the best tutor out there. I already know I'm going to do better. Yeah, you're probably going to do better. But are you going to do better enough to say that his tutelage is significant? Does everybody understand that? So if I said, okay, we're going to do this thing, and now you're going to measure it, but it doesn't have to be a placebo. I'll give you an example of one that I actually did, and I worked with some people, not from a statistical standpoint, but I was working with several people. I've trained many, many athletes. Most of my life I've done things like that. I coached and trained people. I've taught martial arts for almost 40 years. And I worked with a group of people. How many have ever heard of, I think it's called Air Alert? I think that's the name. It was a program probably about 10 years ago. If you're a basketball player, what is, other than practicing shooting all day, every day, what is one thing you can always work on as a basketball player to improve on your own? What do you think? Your vertical height, your spring. And by the way, you're born with a certain set of fast twitch muscles and you're born with a certain limitation. But can you improve upon that? Yes. I can teach you how to run faster. I can teach you how to literally run faster, but I can't make you Usain Bolt if you weren't born with that fast twitch muscle. But I can improve it. I can improve your ability to vertical jump. So this program that was really, really expensive, but I found it online. Somebody had downloaded it because there's a version 1, 2, 3, 4. If you just go to the previous version, it's free online. And I actually did this, and I taught people this. When I would teach martial arts, I would work with people, work with kids. I literally, probably 200 people I worked with. It was a ridiculously effective program. And it's all sorts of kind of weird exercises. I mean, one of the ones you squat down low and you practice your jumping from a squatting position, if you could imagine how odd that is. Pogo sticking, pushing off chairs, all really, really simple exercises that have been tested. But I did this over a course of time, and I was doing this with some really elite athletes, and I was measuring the improvement, and there was significant improvement. Every single person. Okay? Even my own son was doing this because he was playing basketball, and he would notice the spring. And then I would also throw in other exercises. But there's no placebo there, is there? I'm measuring, is this program effective or not? So I don't say, McKinley, I'm going to do this great program, and then I give you a fake program. That really wouldn't make any sense, would it? So measure. Now, are you automatically going to jump higher because you're doing this program? Not necessarily, because that's a physical effect. Believing you're going to jump higher isn't going to make you jump higher. Training your muscles to have you jump higher, you're going to jump higher. That's a totally different. That's not a mental thing. That's like saying, I'm going to talk you into lifting more weight. I'm going to convince you you can lift more weight. You know, that ain't going to work.
Give them a pill that we said would make them jump.
Oh, okay, yeah. Now we're getting in a danger zone here. I like that one. By the way, that is a common thing. If I could give you a pill to improve your performance on the football field or something, I'm pretty sure we have a name for those. It rhymes with lead. PEDs. So the idea, the before and after. So let's do another one now. And probably, funny thing is, even in a stats class, probably the most common one studied because it is the easiest one and has by far the most information out there. Weight loss. Now, there are programs, there are weight loss clinics that you can go to physically. There are programs, you see them all the time on TV, you know, for different types of food. What would be one?
Actino?
Yeah, Atkins, Weight Watchers, Jenny Craig. You've all heard of these. These are legitimate things. These are things that have been around for a really long time and have probably a decent track record. And you're going, yeah, I need to drop a few pounds, you know. Usually it's about this time of year that people are thinking of that sort of thing. You know, right after Thanksgiving, that kind of stuff. And I want to know if this program is actually effective because I'm going to spend money. Now, there's no placebo here. You know, I can't make you think you're going to lose weight. No, you're going to have to lose weight. That's simply a caloric thing, isn't it? You're going to have to burn off more than you intake. That's just simple anatomy, physiology, and a little physics involved. So I have a weight loss clinic, let's say, and I want to deem or to see how effective they are because maybe they're making claims like Biff the Tutor. Maybe they're making claims that don't seem to be supported by the anecdotal evidence. Now, anecdotal evidence is what everybody on planet Earth goes by, and it's dangerous. In other words, everybody knows somebody. I know many people who would not take the vaccine because they knew somebody who got really sick. I've actually met somebody who got struck by lightning, believe it or not. So does that mean you don't go outside during a storm because you know somebody got struck by lightning? I know somebody who won really big at a slot machine. I was sitting there with them when they did it. So does that mean everybody's going to win big at a slot machine? No, actually it's pretty unusual. Everybody knows somebody. That's called anecdotal evidence because, oh, I know somebody that this happened to, and that will sway my opinion. Do you understand how that works? Oh, I know somebody who had a bad experience in this area, or somebody who had a bad experience with that teacher, or they hated that movie. You're talking about one person or one incident. But I know, let's say there's a particular weight loss. I don't want to throw anybody under the bus, but there's a particular weight loss clinic, let's say, and they've been advertising this. But I've met several people who had negative experiences or didn't have that experience. Now, does that mean they're not legit just because I know several people? I've met 5 or 6 people that had a bad experience, but maybe they've had thousands go through their doors. See, that's not enough, is it? But is it enough to at least make you question it? Yeah, so let's go back to like the COVID vaccine. You know many people that had a bad experience and got really, really sick. And you don't know everybody who had it, but you know way too many for it to just be coincidental. So now you're curious, you know, what do the numbers suggest? Are there numbers out there that actually say how many people really get bad reaction? Yeah, we do know that. Yeah, and it's like, I don't know what the percentage is. The last time I read it was like less than 0.001% of people having bad reaction. I don't mean you got sick the day you got your vaccine. I mean you got really sick, like dangerously sick. I know somebody, I have a family member who got really sick and they told him not to take the second shot. But I also know hundreds and hundreds of people that had no reaction whatsoever. I didn't even get the sore arm. I had 0 reaction, and my whole family had 0 reaction. So because I know somebody that had a bad reaction doesn't make it bad. So the whole point is, knowing somebody who had a negative experience at something doesn't automatically make it bad, but it might give you reason to question it, test it. So there's a weight loss clinic that's been making claims. You don't believe it, and you find it really easy to test because you say, can I get into your database and interview several of the people because they actually have, you know, recordings of, one thing they always do, they weigh you before and they weigh you after to see your weight loss. So let's just say a particular weight loss clinic guarantees you will lose, let's keep it simple, 10 pounds. Now, the program, there's multiple types of programs. It might be that they're simply doing a food situation where they give you a lot of them do that, right? They give you the meal plans. And you eat their meals and you do it for an extended period of time, and then over the time you lose this weight. It could be one where you actually physically go to a facility. I knew somebody many years ago, I don't know that they have these anymore, but they used to call them fat farms. Anybody ever heard that term? It was for people who were dangerously obese and overweight, and they would go physically to a place, could be for several weeks. Usually it was on like a doctor's orders, like the doctor said you need to do this or you're not going to survive. And they would go to these places and they would retrain them pretty much how to eat. That was one of the most important things. And they wouldn't necessarily exercise, by the way. You'd think, well, are they going to work out the whole time? No, it was really about eating and patterns. And they would go for several weeks, and then when they would come back, obviously you'd expect them to be a lot lighter and healthier and stuff like that. And usually that was the case. Those kind of places were usually, again, doctor's orders kind of thing, because it's also very expensive, so insurance may or may not have paid. I don't even know if insurance would step in that situation. More often than not, it's probably some form of a meal plan. But they're guaranteeing you. And by the way, when you watch the commercials on TV, they'll always say, you know, you will lose this much weight. So Dylan says, I'm going to do it, and then I'm just going to binge every day to show that. Well, no, you're kind of missing the spirit of the thing. They're saying if you are interested in losing weight and you follow our program, we're going to guarantee you weight loss. Now, is that guaranteeing a weight loss? Ooh. Guaranteeing anything is kind of iffy, do you agree? But maybe that's their track record is this is reasonable. They said you're going to lose 10 pounds. So once again, what are they actually saying?
Lose at least 10 pounds.
You're going to lose at least 10 pounds. Okay? Now, so what happens if you don't? Well, usually in situations like that, if you don't, you can get your money back kind of thing. That's the thing. So the guarantee here would probably be, money back. You're not going to sue them. You spent money, you're going to get your money back if it really didn't work and you were actually trying to do it. Okay? So, let's test at once again, okay. So, what do they say? You're going to lose at least 10 pounds. So we're actually measuring your difference. So what would be the no and what would be the alternative? Well, it's going to look like that one, isn't it?
Yeah.
Oh, yeah.
At least 10, less than 10. So it would have to be significantly less than 10 before you call them on it. Again, you could have a situation where it's really close to 10, but maybe you just had a bad batch, right? You went out and grabbed a handful of people. Yeah, it was close to 10, maybe it was under 10. That doesn't mean they're lying, because the next batch might have been 15 pounds on the average and so on. But what if you grabbed a group of people and on the average they lost 2 pounds or something? You'd say, that's way too far to just be a bad sample, right? That's absurdly far away. Okay? Now, one thing we didn't do here that I want to go back is look at the p-value, just to make sure, because a p-value on a t-test is actually easy because it's just an inequality. I just look, where am I on the t-table? So, let's say this time we go out and we collect a sample of size 12, because I want to use different numbers than the first time. So if we do a sample of size 12, what is our t-value that we're looking at? Well, how many degrees of freedom? 11. And at the O5 level, 11 degrees of freedom, what's our magic number? Yeah, it's a little bit smaller than the previous problem, isn't it? Because it's higher degrees of freedom. The more degrees of freedom, the lower that number. In fact, as I raise this number up and up and up, this number will get closer to 1.645. Oh, that would be the z number, wouldn't it? But I don't want to use the z number because it's going to be a t-test. So what will cause us to reject the null hypothesis? So we will reject the null hypothesis if the measured t is less than negative 1.796. So if our improvement isn't good enough, not close, it has to be fairly far, okay? This was really far, wasn't it? Okay? Let me erase this. So we went out and got 12 people. All right, and I'm just going to number. It doesn't matter male or female. That's irrelevant. So this person started off at 175, and afterwards they were 160. This person 148, and afterwards 143. This person 236, and afterwards they were 212. Big improvement. This person here was 216, and afterwards was 220. They snuck in snacks. By the way, is that a possibility?
Yeah.
Yeah. Yeah, I've actually known people that they tried to do a weight loss thing and had an allergic reaction, swelled up like a blowfish. Water weight, but still they gained a lot of weight on the weight loss. That's unusual, by the way. Unusual. This person was only 98 pounds and they got down to 96 pounds. I don't know why they were there. 137 and they got down to 120. This person was 182 and got down to 179. This person 263 and got down to 248. This person 197 and got down to 195. This person 167 and got down to 162. This person 138 and got down to 128 exactly. And this person here 109 and got to 103. Okay, these are my 12 samples. But if I subtract, won't most of my numbers be negative? Right? So how did you do? Oh, my weight loss was negative 10 pounds. You wouldn't say that. If you lost 10 pounds, you don't say my weight is negative 10. You say I lost 10. Anybody ever go diving? I used to be a diver way back in the day. And you don't say, oh, I was negative 20 feet. No, you say I was 20 feet below the surface. You measure 0 here, and you measure positively as you go down, don't you? You don't measure how far from the ocean floor you are. Oh, I was 25 feet off the ocean floor, but I was 3 miles deep in the water. No, you measure how far you are from the surface. So you're 20 feet deep, I'm 100 feet deep, I'm 50 feet deep. Does everyone understand you measure going the other way? So how do you measure weight loss? How much weight did this person lose? 15, not negative 15. So, before what did we do? We said after subtracting before because we were measuring improvement. So the previous example, wasn't the second row all way bigger than the first row? I remember it was your scores. First row was your percentage before, the second row was your percentage afterwards, and we were measuring improvement. So we subtracted in such a way to get positive numbers because that's what we were measuring. But now we're measuring weight loss. So wouldn't you say losing 10 pounds is a good thing? Yeah. So now we're going to go before minus after. We're subtracting in the opposite order. This is what I was pointing out before. You got to know which way you're subtracting. Because improvement in this case is you weigh less. So would you say this person improved by 15 pounds? They didn't gain 15 pounds. They lost 15 pounds, which was their whole goal. That's really important that we recognize that order of subtraction. So when I'm looking at weight loss, now this is, keep it simple, 15, 5, 24. What did I write for this person? I actually put -4 because that does matter. They gained weight. They went in the opposite direction. That would be kind of like going to Biff the tutor and having a lower percentage afterwards. I have to count that negative number in my calculation. That one right there can really mess us up. 2, 17, 3, 15, 2, 5, 10, 6. And that -4 is important. just like the 24 is important. You'd say that's kind of extreme, well, so is that one. But maybe those extremes balance out. Okay? I don't want to erase that quite yet. Let's do it right underneath. So now we need to find what is the sum of my differences, what is the sum of the square differences. So let's add those up first. It's exactly 100? Wow, I'm good. Okay, so we got 100 for this. All right, I have a number for the second one. That's what I was doing. Tell me when you get the second one. You know, it's funny, the newer calculators, it's harder. The old cheap calculators, way back when, it was really easy to do this problem. You had the ability to just simply enter it. Now, this calculator does have the ability to enter it, but finding some of the other cases where you actually could just enter 15, 5, enter the numbers, and then there'd be a key. You could ask it for the sum, you could ask it for the sum of the squares, you could ask it. So what do you got?
1,502.
Close.
That's what I got.
You guys subtracted this. No. When I square negative 4, what is it?
16.
Positive 16. You guys subtracted 16.
I put in plus -4 squared.
Right. But you went negative 4 squared instead of... I know that because every group does that. In other words, if you did this, you subtracted 16 when you want to actually add 16. The simplest way to do that is ignore the negative and just do 4 squared. Yeah, I did this on purpose because everybody has issues with variance when you have a negative number. Because you got to square the negative number, not minus 4 squared, because then you're squaring the 4 and you're subtracting. So you guys are close.
1,800, no, well, 1,534.
34, yeah. That's why I was doing that. By the way, you just demonstrated the single most common error in calculation. When you're doing a variance and you have negative numbers, you have to square the negative number. But you said, but that's so hard on my calculator. Well, if you're squaring a negative number, isn't it the same as squaring a positive number?
Yeah.
So just square the positive numbers. Don't even enter the negative. But when I was adding these, I had to add -4, right? That's important that I subtracted 4. But in variance, it's the sum of the squared values. So now the sign doesn't matter. Okay? So that's kind of important. Now, let's continue. So what is my x bar of the differences? Well, it's 100 over 12, which does not reduce nicely, so we'll just leave it like that. The variance of my differences is then 1534 minus 12 times 100 over 12 squared over 11. Okay, so tell me when you get a number. I'm going to leave the number on my screen for calculation, but this is approximately what?
I got 63.7.
Yeah, I got about the same thing, about 63.7. Now, that number in and of itself doesn't mean anything to us, but I'm going to use in my next calculation because when I calculate my t, I need the standard deviation, so I'm going to need the square root of this number. Okay, so now, my t star, well, what are we saying is the truth? That you are going to lose 10 pounds. So my x bar, I'm not going to enter a decimal rounded off number. I'm just going to enter a fraction. It's easy. Minus 10 over the square root. In fact, I can just write it like this. 63.7 over 12. So whatever's on your screen here, Square root answer equals. Tell me when you get a number.
Negative 0.72.
Good. About 0.72. Now, that's negative. That's in rejection zone, right? Well, what was going to give us rejection? Anything below negative 1.796. Where are we? You know, we're somewhere in here.
Do we square root the n?
Yep. Remember, it's always standard deviation over root n.
Yeah.
But since I got to take the square root of this anyway, I can just put the whole thing. Remember, it's square. This is your variance of the sample always, or in this case, s squared. Oh, okay. So I already got the number, so it's just easier if I write it like this. Now, that number is negative. Is it negative enough?
No.
Do we reject it? Yeah, I mean, here's the shark-infested lava on the other side. Right, you were full sprint, but you stuck away with it. You're really not very close to rejection, are you? So, first thing is what? What are you going to say? Reject the null or fail to reject the null? Fail to reject the null hypothesis. Now, are you buying the claim, hook, line, and sinker? Or are you saying absolutely they're telling the truth? Well, you know, my average weight loss, 100 over 12 is only a little more than 8 pounds per person. They're guaranteeing you're going to lose at least 10 pounds. And my sample, they were only losing 8 pounds. But it wasn't far enough away for me to say there's a false claim. But am I going to overwhelmingly embrace their claim? Oh, heck no. No, this is one of those not enough evidences. If the average in my sample exceeded 10 pounds, then I have no problem saying, yeah, they're totally okay making that claim. Yeah, my sample verified it. But they were less than 10. In fact, 8 pounds is not huge, but it's less than 10. I don't feel comfortable guaranteeing that this claim is correct, but there's not enough to find them guilty. So we're setting them free, but we're still cautious. So probably the best thing to say is, not enough evidence. Not enough evidence to conclude what? To conclude
You will lose 10 pounds.
you will lose.
At least 10 pounds.
No.
Oh.
Not enough evidence to conclude this, so not enough evidence to conclude you'll lose less than 10 pounds. See, they're guaranteeing you're going to lose at least 10 pounds. We tested them. We don't believe them, but we weren't extreme enough. This is not statistically significant. So we couldn't disprove their claim. We couldn't say they're lying. We couldn't say you're going to lose less than 10. There's not enough evidence to conclude you're going to lose less than 10. But that doesn't mean we're wholeheartedly endorsing them. We're just saying not guilty. We're not saying innocent. What would be the innocent would be if our sample actually exceeded 10 pounds per person. That's these guys are legit. They're telling the truth. Man, they're even better than they're claiming. That's what our sample would have had to look like. Agreed? That's the part I want everyone to see. The not enough evidence to conclude that the alternative is the truth is the safest one in this case. Now, this would have had to been way more extreme. Now, let me ask you kind of a question. Is it possible they are legit?
Yep.
We find out later this person works for a rival weight loss company. They're having some fun with you. What if we took that person out? I don't mean take them out that way. I mean, what if we remove them from our sample? This would now be 104 over 11. That's about 9.5. Right now it's 8.333. That's about 9.5 now. Does that make you feel more comfortable with them saying, yeah, this is really, they're legit? If my sample came in a half a pound less than that, I don't have a problem saying, yeah, it's reasonable to say that this is true. But again, this is obviously an outlier. You cannot remove outliers. But you understand that, you know what, that outlier did affect the final conclusion. How do I minimize the effect of outliers? It's real simple.
Larger population.
Larger
Large sample.
sample. Okay? I would have, if I'm actually doing this and I want to report this on the news and stuff, I think I'd want more than 12. I think I'd want 100 or something. But it may not be that you have access to that many. It may be that you just, this is all you could do. Because if we're looking at their records, the before and after, is this a lot of work on our part? Not at all. But what if we're actually testing people and saying, let's say it's one of these meal programs, which is probably the most popular kind. So I actually got a whole group of people that said, yes, I will go ahead and do this. Why would I have a small sample? Because it's expensive. So I have maybe I'm paying for it. And so I got 12 people to agree to do this for however many weeks it takes. And we wage it before, we wage it at the end. That part's easy. But I had to wait a few weeks to do this. I had to spend a lot of money because I had to purchase the program for each of these people who volunteered, and then I measured it. So that's a reason why this might not be a big sample, just because of the cost aspect. Does that make sense, everyone? You say, well, what could it possibly cost? I'm guessing, I don't know, a couple $100 a week per person. I've never been on a meal plan, but I know how much it is to feed my own family. Yeah, so in other words, I wanted to do this for however long it takes. It's probably several $1,000s. Yeah, and I'm the one doing the testing. I'm not getting reimbursed. Yeah, I'm probably not going to go with 100 sample, right? If you want to volunteer and pay for it, I'll do 100 people. Now, let's talk about the p-values in both of these. Because p-value, when it comes to a t-test, we know what to do with a z. We go right to it. It's real easy. But with a t, all I have are inequalities. So in the first case here, the p-value, remember, is equal to the probability of a result this extreme or more. So it would be t being less than negative 3.4. That's what the p-value would be. I can't find that value exactly in my table, but I can look in my table and say, all right, now, for 9 degrees of freedom, look at the numbers on there for 9 degrees of freedom. Now, negative 3.4 is in one direction. Think of positive 3.4 is in the other direction. Look at 9 degrees of freedom. The very first number is 3.250, and then the numbers go down, don't they? So to have a number that's bigger than 3.250 means you're going to go to the left, but you're already at the 005 level. So that means this is less than 005. That's how you read it. Look at your table. Look where this would fall. By the way, the positive and negative isn't the thing when you're looking up a p-value. It's just how big is the number. Does everybody follow that? Oh, our level of rejection was at the 5% level. The probability, if the claim was true, if the null was true, the probability of a result this extreme or more is less than 0.05. That means you are very confident in your conclusion. You rejected the null because this is extremely unlikely that the null was true and have a result this extreme. Now, let's go to 11 degrees of freedom and look at the number 0.72. For 11 degrees of freedom, where does that number fall? Way to the right, doesn't it? So going to the left was getting smaller, going to the right was getting bigger. So in this case, your p-value, which would be the probability of a result this extreme or more, would this be a less than or a greater than?
Greater than.
This would be greater than, and greater than what number?
0.10.
Perfect. That's a perfect answer. Now, I don't know, without the use of a computer, I cannot tell you the p-value. But we know it's bigger than 0.1. So saying, if the null were actually true, then results this extreme can happen often. That sometimes makes you feel more comfortable with your not rejecting the null. Saying, you know what, this is not an unusual result at all. I don't know what the p-value is, but I guess it's probably closer to 0.2 in actuality. And you're saying a result, this extreme can happen 20% of the time if they're telling the truth? Well, yeah, okay, I can live with that. I can live with the, I didn't reject it. Maybe they are telling the truth. Okay? Everybody good with this? This is not complicated. What was different in these problems is you actually have to calculate the mean and the standard deviation because all you have is sample data. That's why in the textbook, the author does a great job, by the way, with the problems. This is section 9.3. In the problems, he gives you several sets, and he does it just like I do, the before and after. But in every case, I'm looking at these numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In almost every problem, he uses 10 or less pairs. So you can kind of, fast forward through every problem. Some cases, he only gives you like 5 or 6 pairs of things. Okay? Can anybody think of a situation in real life where you could see that this would be useful to make a conclusion in anything? Does anyone here take supplements, for example? For anything? What do you take supplements for?
Creatine.
Okay, so this would be a really easy one. Measure your performance before you started taking the supplement. Take the supplement for a while. Measure your performance after the supplement. Is that a simple thing to do? Yeah. Now, the problem is you're a sample of size 1. So to know if it's effective, you probably would want lots of it. But that's exactly how it starts. I wonder if this is effective.
You got to.
Oh, okay. But do you guys understand what I'm talking about? So if you said, is this effective? I don't know. And here's one of those odd things. It works for me. Sometimes that's good enough. But then you start doing the research and you look at the data and going, oh, okay. Maybe it is, maybe it isn't a good thing overall. But I seem to have success with it, and sometimes that's good enough. You have never done it before. So now you're looking at, you're going online, you're looking at success. So now you're looking at probably what are called case studies, the before and afters, measuring people, and they're saying, yes, these are measured performances that we see. So why, it's an interesting question, because there are a lot of sports fans in here. Why are PEDs banned? Why are they looked so down upon?
Because it puts you so far ahead of people that ain't taking it.
How do you know?
Statistics.
Because the evidence actually bears that. Yeah, a lot of people say, well, how do you know? How do you know? I mean, I've been using steroids my whole life and I don't have any positive effect. He's like, how do you know they improve performance? Because it has been measured over and over and over again. We have the statistics, we have the data to show the performance. And plus, we have the anecdotal data. I'm going to throw one out at you. How many have ever heard of Ben Johnson? For about a minute, he was the fastest man in the history of the world. 1988 Summer Olympics. Now, the world record holder at the time, Carl Lewis, broke the world record in the 100 meters. And he also was multiple gold medalist in the long jump. One of the greatest athletes of the 20th century, Carl Lewis, because he was the greatest long jumper and the greatest sprinter for probably a 10-year period. At the 88 Olympics, Ben Johnson broke the world record, but his name is not in the record books. In fact, you never heard of him again after the Olympics. You've heard?
He got popped for PEDs.
Yeah, the guy had never won a major race. There was even questions how he made the U.S. Olympic team, and then he breaks the world record in the 100 meters at the Olympics, running so much faster than he had ever run in an actual major race. And so, of course, they tested him, and he was glowing in the dark from all the steroids, and he was then banished. When they banish you for life, it's usually like a year, then you can appeal, but he pretty much never came back. He lived in shame because his performance was so far over the top of what he had ever done before that even if you said, well, steroids don't help you, well, they helped him. They helped him a lot. Now, interestingly enough, a couple of Olympics later, some Americans got in all sorts of trouble. And the funny thing is, American sprinters for years, it seemed like every time we had a good one, they were getting popped for cheating. And then they'd come back a few years later. But we had a female who basically threw everybody, including her husband, who was no longer her husband, he got caught at the Olympics and was banned. And she threw everybody under the bus. Anybody ever heard of Marion Jones? She was the greatest American sprinter for a while. Won multiple Olympic gold medals, and then finally was found out that she'd been cheating the whole time and banished for life in infamy after she threw everybody under the bus. The problem is it's hard to catch people, for one thing. Because generally, the cheaters are way ahead of the
So bad.
testers. No, the cheaters are always way ahead of the testers because you're testing stuff that was, 5, 6 years ago, and you're on to the next thing. But the thing is that how do you know that they actually work is that we have stuff. Now, I'm not going to say pro or con PEDs, because if that's what you're going to do, that's what you're going to do. But the evidence shows it helps. By the way, did you know creatine was banned for many, 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 many years? It was considered a performance-enhancing drug. People, yes, yeah, it was very looked down upon for a very long time. People treated it literally like it was steroids. Now, I think there's been enough evidence now in testing, now they're saying, no, it's not. But 20 years ago, you told someone you were on creatine, you might as well be using steroids every day. That's literally the reaction you would get. And if you were a professional athlete, you might be actually suspended from your sport. Wow. Yeah, things have changed. Okay, so it's an interesting thing. The before and after is kind of fun though, because you can now look around. There's so many things you could measure. The simplest things are like athletic performance. I'm on a program to do something, and I have a son who's a very, very avid weightlifter, and keeps track of everything. And he actually weighs his food. We have one of those little tiny scales. He weighs everything before he eats it. It's kind of ridiculous. He'll pull a grape out because there's one too many grapes. But he measures everything, and when he starts a new program, he's got data records and everything of the improvement and the performance, and is this working or not working. But he doesn't decide after one session, over several weeks. And basically he's doing statistical studies, but on a sample of size 1. So that's where I got back to before. It's not even important if this thing works for the general population, it's does it work for you? And so you can actually do your own statistical analysis if it's just you and you want to know, does it work? But let's say it does work for you, and then you share it with somebody else and it doesn't work for them. Then it's probably not going to go much further, is it? But you share what you're doing with somebody else and it works for them, and it works for the next person, it works for the next person. Now you say, hey, is this a legitimate thing that everybody can benefit from? And that's usually how things like this get started. It's the before and the after. Okay, you can go ahead and stop that. All right, we'll take a break. I want to do a couple